Hi, this is Kevin Trainer. Welcome to my lecture on Chapter 10 of Murach's third edition MySQL book. Chapter 10 is about how to design a database. As usual, I'm going to leave the objectives for you to read on your own. When we design a database, okay, um, our objective typically is to create a data store that does a good job of holding information about things that we care about that we want to refer to typically in our work lives, but it could be in our personal lives. It could be things related to entertainment and stuff. So the diagram that we see here is really saying that we've got things in the real world, okay? Um, Maybe we already think of them as an information system, and maybe we don't, okay? And what we want to do is we want to look at that real world and we want to say, well, what's of interest for us to capture data about right now, okay? Or in the near future, okay? And then we use that to drive the decisions that we're going to make about how we're going to model that data and then how we're going to go about the design of the database, in this case, a relational database. And Murach introduces a recipe for designing a data structure that's a good one. You can imagine, okay, if you've done really any cooking at all, that some recipes are kind of simple and some recipes are much more complex. And if you're, let's say you're a fine chef, if you were really to write down all of your steps, you probably would have a pretty long and complex recipe for how you make one of your fancy dishes. Okay. In terms of recipes for designing a data structure, the version that we see here from Joel Murach is kind of in the middle. It's not ultra simplified, but it's kind of simplified. In my class, we're going to eventually get to a recipe that I put together within the last couple of years, and it has many more steps than this. But this is a great one to start out on. So here are the steps. Identify the data elements, subdivide each element into its smallest useful components, identify the tables and assign the columns, identify the primary and foreign keys, review whether the data structure is normalized, and then uh, identify any indexes that you're going to meet. In this case, he probably means additional indexes. So, in this kind of, let's see, this is kind of systems analysis work. And one of the things that we do when we do systems analysis is we go out into the environment that we're working in, and we look at the data that's hanging around there, and we use it as kind of fuel for our data modeling process. So here, what he's trying to do is um, he's trying to model accounts payable data. In the textbook, our primary example database is the AP database, an accounts payable database. And he's kind of showing us how you might have come up with a design of that database. Okay, so here's an invoice. It's from Acme Fabrication. Okay, and It's to us, so I guess we're uh, custom contraptions, contrivances, and confabulations, I would assume. And it's coming from Acme Fabrication. Okay. And it has the typical things that you would find on an invoice. It has the number, the date, the payment terms. It has the name and address and phone numbers and URL for the company that sent us the goods or services. And then we have a bunch of lines on the invoices, which include a part number, a quantity, a description, a unit price, and an extension. It doesn't look like, oh, there's a line also for sales tax. There doesn't seem to be a line for shipping. There's a contact. There's our contact is our sales person. Oh, we have a contact name for the salesperson and for the accounts receivable. And we have a total. Please pay this amount. Okay. Um, if in fact we're going to put together an accounts payable system that's going to help us to organize the invoices that we're going to pay, this would be a key document that we would analyze when we would be coming up with the design. So one of the things that you can do is take a key document like this and break down the data elements that are on the document. So he's got a list here: vendor name, vendor address, vendor phone number, item quantity, item description. And you'll notice that the way he's naming these data items is maybe a little more general than they appear on the invoice, right? For instance, Acme Fabrication is the name of the company sending the invoices. Well, in our context, they're a vendor. So vendor name, vendor address, vendor phone, and all that kind of stuff. That's not what it says on the invoice, but that's how we would think of the data. So those are pretty much the items that are on the invoice. One issue that comes up, and we've talked about this quite a bit in my class, is when you go to store things like names and addresses, you probably want to disaggregate them. Okay, so here's the name: vendor sales contact name Ruben Goldberg. And it looks like he's decided at this point to break it into two parts: first name and last name, with the idea that when he wants to use it as a whole name, he'll reconstitute it in the query using the concat function. Okay, here's an address, the same thing. So the vendor address appears on the invoice really completely aggregated, but he's decided to store it disaggregated into street and number, city, state, and zip. And I think that's a great idea. We've already passed the chapter where we were trying to use the string functions to disaggregate person names. And that's pretty easy for very simple names, but it's very difficult for the challenging ones. So let's see. He does a little thinking. He says, well, here are the possible tables and columns that he sees for an AP system. Okay. And what's kind of interesting here is in a more sophisticated approach to data modeling and database design, which is one that we take in my course after we finish the Murach book, we actually start a little bit earlier. I mean, we're not really trying to design in our first pass. We're not really talking about tables. We're talking about data modeling, we're talking about entities and relationships. We're not talking about columns. We're talking about attributes. He's kind of left that conceptual data modeling step out altogether and gone right to relational database design. Do people do that? Yeah, especially especially when they're new, and especially when uh, they're not really trying to come up with a real sophisticated design. Okay, so this is kind of database design simplified. Okay, so he's saying he's going to have a vendors table and invoices table. And again, he comes from the school where he thinks that relational database table names ought to be named in the plural. I come from the school where I believe that they ought to be named in the singular. It's probably because I come from the school where the first thing we do is conceptual data modeling. And it's pretty clear in conceptual data modeling, we don't have a vendors entity, we have a vendor entity. Okay, so, but what he's done is he's taken all of the fields that he can find in his documents related to vendor, and he's put them on the vendors table. He's decided that some of these he's maybe not interested in, so he's crossed them out. Okay. He's also decided on some of these things that he's going to uh, he's got some things that I forget what the key is. He does tell us here. Okay, here's a notation. The data elements that were previously identified but aren't needed are crossed out. I'm right about that. The data elements that were added are displayed in italics. So these are data elements that weren't actually on the invoice or the other documents that he had, but they make sense in terms of the application. And data elements that are related to two or more entities are followed by an asterisk. Okay, that's going to be important to us because in a good relational design, we keep all of the columns that have to do with one entity in one table. And so, to the extent that we want to have relationships between tables, we're going to use foreign keys. Okay, so he's got all these on invoice line items. Here's the notation. And now he starts to talk about the relationships between tables. Now, whereas this is an interesting notation that he uses here, I can't think that the relationship notation that we have here is from any formal system. It's just one that works out well in terms of the diagrammer that he used to create the diagrams with. So the dot end is a one end, and the triangle end is the many end. So he's saying for each vendor, we have many invoices. For each invoice, we only have a single vendor. And he's saying for each invoice, we have many invoice line items, but each invoice line item is for only one invoice. Okay. Now the notation that we're eventually going to use in this course is a little more detailed than that, but that's what this is supposed to mean. Okay, so one-to-many relationships are easy to understand, and they are directly modeled in relational databases. You get into challenges when you have many-to-many relationships because we have to model them indirectly in relational databases. And we do this by creating a linking table or an associative table. He calls them linking tables. So this is a really nice example of a place where you would have an associative or linking table. We have a table of employees, and we have a table of the committees, and then we have a table called memberships. So each membership connects an employee to a committee, and it's many to many in the sense that each employee can be on many committees, and it's many to many in the other directions in that each committee can have many employees. And what do we do with the linking table? Well, at a minimum, they have two foreign keys. Okay, so they have the foreign key that points to the employee, and we have the foreign key that points to the committee. And you can really think of this as um, um, it really takes the relationship and it makes it concrete, okay, in a really, really interesting kind of way. So, at a minimum, linking tables have to have uh, uh, a foreign key that points to each of the primary tables involved in the relationship. Could they involve other columns as well? Yeah, they can, and they often do. Okay. Um, a lot of times there's information about the relationship between this employee and this committee. For instance, the date that they joined the committee. Okay. Maybe the date that they resigned from the committee. Okay. Those kinds of things. All right. So it's not uncommon for these kind of relationships to carry extra data, in which case there would be columns for that. One question that comes up is what's going to be the primary key for the memberships table? And there are a couple of approaches to this. One is that we say that the primary key is just the combination, it's a composite key, and it's the combination of the primary keys of the two primary tables that we're trying to relate to each other. So that the primary key for memberships is employee ID and committee ID. You might find in the Joel Murach book a place where he says, well, they don't have a primary key. At least his last edition said something like this. And in this respect, he's really in the minority. If you do research, you'll see that most relational database experts would recommend that these linking tables or associative tables have a primary composite key that it's composed of these two foreign keys. The other thing that you may see is this kind of table might have its own key. It might have a surrogate key. So it might have a membership ID. Okay. One of the things about this having its own key is that one, you don't have to use the two foreign keys to make up the primary key. The other thing is there are a lot of applications like this where you want one employee to be on a committee more than one time. Now, in terms of employees and committees, that doesn't work, okay? But it works really well in terms of pizza toppings, okay? If, in fact, we're trying to connect orders for pizzas with pizza toppings, Is it possible that we want double pepperoni? Okay, yeah, it is possible we want double pepperoni. In which case, having your own primary key on the linking table, which is typically just a simple integer key, allows you to have more than one connection between the row, a particular row in employees, and a particular row in committees. Here, in this instance, I think the design is just perfect the way it is because you're either on the committee or you're not. Okay? So that's a linking table to implement a many-to-many relationship. Here's two tables with a one-to-one relationship. So we have employees and we have employee photos. And so we can see that some of the columns on employee are first name and last name. Um, Employee photos also seems to have the a primary key of employee ID, and then we have employee photo. Now, I'm going to tell you that generally speaking, one-to-one relationships are suspicious. Okay, well, why is that? Well, uh, I just want to point out that let's see, employee photos. Um, okay, but we might have a situation here where we would want to be able to have more than one photo for the same employee. Okay, so that wouldn't be one to one, right? That would be one to many, potentially. So that's not one to one. Okay. Um, we also could have maybe it's optional. Okay, so maybe it's not always one to one. It's a situation where for one employee, there's 0 or 1 employee photos. Okay, and maybe the employee photo is a big blob. Okay, so it's a really big field. Okay, um, there are times when even when they're not optional, people would like to design them into their own table. So you could see that. But the fact is, if there is always one and only one employee photo, and it has a modest size, okay, and it's not optional, uh, I think there's the strong argument is for moving employee photo over to employees. So there are certainly size considerations and those kinds of things that can get you to move to split up a table. But I'd really like you to think of this as a proper employee table that because of implementation considerations, we decided to split. Okay. Operations that can violate referential integrity. Okay, so each of these relationships that we have is implemented by a foreign key. Okay, um, so in the case of the many-to-many, the foreign keys are in the linking table. Their employee ID points to employees, and committee ID points to committees. Right. Okay, so when we have foreign keys, all right, if we don't manage them well, we can get the database out of whack. Okay, which is we basically can be pointing to a row in the other table, and that row isn't there. Maybe it was never there. Maybe it was there and then they deleted it. Maybe it was there and then they changed it. Okay, so it's very important to maintain the referential integrity of these tables, which is to say the foreign keys should always point to a row in the pointed to table, and we can't get the situation where they don't point correctly anymore. That would be a lack of referential integrity. Okay, and in relational databases like MySQL, we have these things called foreign key constraints, in which we set out the rules for how much the database server is going to check for and enforce these integrity rules. Okay, well, here's how things could go wrong. Okay, deleting a row from a primary key table. If the foreign key table contains one or more rows related to the deleted row. So this is a situation where we were pointing to a proper row in the table, but now that row's gone. Okay, we don't want that to be able to happen. Inserting a row in the foreign key table. If the foreign key value doesn't have a matching primary key value in the related table. So let's say we wanted to insert a record that says that Kevin Trainer is teaching course 1, 2, 3, and we go to the course table, and there is no course 1, 2, 3. Okay, well, that's the kind of insert that we should reject, because it would leave the database with damaged referential integrity. Updating the value of the foreign key. So if the new foreign key value doesn't have a matching primary key value in the related table. So suppose we said Kevin is teaching course 1, 2, 3, and we go, oh no, that was really supposed to be 3, 2, 1, and we change it to 3, 2, 1. But there is no course 3, 2, 1. Well, again, that would violate referential integrity, and we want the rules, the constraints for the database to be set up such that that kind of update would be rejected by the server as invalid. And updating the value of a primary key. It's not often we update the value of primary keys, but if the foreign key table contains one or more rows related to the row that changed. So that's a very good reason to not be changing the value of primary keys, because we don't want rows in other tables to be pointing to a row in the primary table only to find out that it's not there anymore. Okay, it has a different foreign key. All right, so this referential integrity is essential to relational database health. The way that we're going to learn how to enforce that is to set up foreign key constraints on each of our tables that use foreign keys. And we're going to rely on the database management system to enforce the rules that are implied by our constraints. Terms to know about data structures. An entity, typically we talk about entity types, okay? An entity type is a type of thing that we're interested in the real world, okay? So we might be interested in orders and invoices, or warehouses or customers. Okay, so each of those is an entity type. We differentiate them typically from entity instances. So we might have an entity type that's a customer, and the instances could be Kevin and Mary and Ann and Bob. Okay. Typically, in a relational database, entity types get turned into tables, and entity instances are represented by the rows that we insert into the table. Attributes. Attribute is a data modeling word for a data field. Okay. So in relational databases, each attribute of an entity type uh, gets turned into a column in the relational database. We've already talked about instances. So in relational databases, again, uh, the entity types become the tables, and the entity instances get represented by the rows of the table. Entity relationship modeling uh, is a way of representing the entity types and the relationships between them and the data attributes of um, the entity types that we're interested in. Those are often represented by entity relational uh, diagrams or ERDs, and these couple of slides we had. This is a rough entity relationship diagram, a rough ERD. These things here. Okay. Referential integrity has to do with uh, the need for the foreign key references that we use on uh, rows in the database to actually point to proper rows and other tables. Declarative referential integrity is the way it works in uh, relational databases like MySQL. We declare the rules of referential integrity in these foreign key constraints, and then the database management system sees to it that those rules are enforced. Foreign key constraints, again, is the way that we implement declarative referential integrity. And um, an orphaned row would be a row in a table that has a foreign key that points to a primary key table, but that row in the primary key table is not there any longer. Okay, and if we wanted to use the true sense of orphan, we would say that maybe that row had been there when we added the relationship, but was subsequently deleted, and we've left the row pointing to it as an orphan, a child without a parent. Okay, but in its wider sense, it relates to any row that points to a primary table um, and points to a row that's not there. Okay, so it breaks referential integrity. Okay, so now we're gonna kind of look at the data that is related to this accounts payable application, and we should kind of recognize it because we've been using these data in the textbook all along. Okay, we've actually been using the AP database as designed by Joel Murach. And now he's kind of taking you through his process for designing it. And he says, when he starts, he might have tables that are not normalized. Okay. Normalization being a property of relational databases relational database designs such that, um, generally speaking, we put data in the proper table and we don't keep redundant data. Okay, so he starts here. He's got a table that contains repeating columns. So he's got a vendor name, Connor's Publishing, an invoice number, and then he's got three items on the invoice: an Android ad, a MySQL ad, and a library directory. So he's got the three things there. Okay. It turns out that one of the rules for properly designing relational databases that meet these normalization standards is we don't have repeating columns. Okay. And one of the ways to think about that is it's just not the relational way. It typically, uh, if you have repeating columns, then you change your design to put the things that repeat in a separate table. Here's another design, a table that contains redundant data, where we have the vendor name, the invoice number, and the item description. And it looks good, okay. It doesn't have the problem that we have repeating columns, but we do have the problem that the vendor name, for instance, is redundant. So we've got Connor's Publishing there three times, Zilka Design there three times. So those are redundant values in a field. And the problem with redundant values is that if in fact we decide that maybe Connor's Publishing is misspelled and it should have been Conner apostrophe S, well, then we have to go change it in all the rows in which we had it. And that is a mess. And that's the reason that that's not the relational way. So putting values, say, typed in text values into columns like vendor name is not the relational way because it creates redundant values. Okay. Okay, so let's see what we do. This is the accounts payable system in third normal form. This is about the way it is uh, in the actual database that we use with the textbook. Okay, so what did he do with the vendor name? Well, he put it onto vendors. Okay, and then for a particular invoice, how do you know what vendor it's associated with? Well, you look at the vendor ID on invoices, and that's the foreign key that points you to the vendor, the row in the vendors table from which you can pull the vendor name. Okay, and we've been doing this throughout the course in terms of using the AP relational database. Okay, well, why did everything get over to the vendors table that did? Well, these were all things that related to vendors. Okay. The other thing is we had things repeating. Okay, so we have these, instead of having repeating columns, we have these invoice line items. Okay, so we can know what invoice ID each one's for. Then there's a sequence. That's probably the line item number. And each of those is going to be charged to an account in our general ledger accounts. So account number here is a foreign key. And then there's a line item amount and a line item description. So, terms to know about normalizing a data structure. Uh, Normalization is again a uh, goodness quality of relational database design. Uh, it really has to do with, as soon as I give you a number, I'll say really has to do with three things, and then I'll think of a fourth. But I'm going to go on a limb here and say three things. It has to do with three things. One is it's doing things the relational way. Okay, no repeating columns. Okay, repeating columns are not the relational database way. That's just not the way we do things. Okay. Uh, the second thing is that uh, we put columns on the right table. Okay. And there are a lot of fancy rules of normalizations that really comes down to the issue of, does this column really belong on the vendor's table or does it belong on the invoices table? Okay, and there are a bunch of normalization rules that you could use to make sure that you've put it on the right table. One of the things that I try to do is I try to get my students to really kind of think about all of the columns or the what in conceptual data modeling we call the attributes, uh, where they really belong. What do they belong to? For instance, if we go back a little bit, where does the vendor name actually belong? Well, it really belongs to a vendor. Where's the vendor address really belong to? What does it belong to? It really belongs to the vendor. Is it of interest in invoices? Sure, it is. Okay, which is why we put the vendor ID foreign key field on invoices in order to allow us to go get all the vendor related fields or columns that we need when we're, say, printing an invoice or processing an invoice. Okay. So a lot of the relational rules have to do with, have we put the column on the right table? Okay. Uh, the third thing has to do with redundant data. Now, to a certain extent, having repeating columns can cause redundant data. Also, uh, putting columns on multiple tables and instead of finding the one right table that they go on and placing them there, well, that can cause redundant data as well. Okay, but generally speaking, we don't put any data into the design that can be derived from the other data that we already have. Okay, and um, I'm looking at the design that we have in front of us here. And do we have an invoice total? I don't think we do. We have an invoice number. Oh, yeah, we have an invoice total. Now, in a truly normalized relational database, okay, if we had a series of line items, uh, and each of them had a line item amount, okay, and you could add them up to get the total for the invoice total, we would consider it to be not uh, normalized to also carry the invoice total because these two facts, the sum of the line item amounts and the invoice total amount, could begin to disagree. Okay? So, in truly normalized relational databases, which this is not, we wouldn't carry an invoice total. And whenever we um, whenever we wanted to know the total for the invoice, we would sum up the totals of the line item amounts. And for those of you in my class, you'll recall that that's what we do in our My Guitar Shop database. We don't have an invoice, we don't have an order total on the order, okay? And we have to go to the order items and sum them up in order to figure out what the order total is. And that's a more properly normalized relational database. Okay? So, an unnormalized data structure uh, is one that breaks some of the normalization rules. What could it be? Well, it could have repeating columns. That's probably not a good idea because you don't get a lot of gain from that. Okay. It could have columns on the wrong table. Well, there's not a lot of gain from that either. But there are times that people do things like we just saw, where they decide that they're going to want to use the invoice total frequently enough that they'll denormalize the design and they'll carry redundant data where, again, they have to make sure that the invoice total on each of the invoices is always equal to the sum of the line item amounts. Okay, that's there are times when people intentionally do that denormalization in order to speed up processing. Okay, so that's an unnormalized, well, that's actually a denormalized data structure. A normalized data structure follows all the rules of normalization that you want to follow. It turns out that normalization has a lot of shades. Okay, the ones that we've talked about so far are first, second, and third normal form. Most online transaction processing databases are normalized to third normal form, and that's kind of what we're seeing. Okay, so that's what a normal form is. When to create an index. Okay, now, in most relational database products, okay, as soon as we say that we have a primary key, then that primary key has an index. Okay, so we don't have to explicitly say build a primary key index for the customer table. As soon as we say we have a customer table and the customer ID is the primary key, MySQL will automatically see that a primary key index is generated for that key. Likewise, um, we also need foreign key indexes. And foreign key indexes allow us to easily navigate across relationships both ways. Now, it's easy to see how one way works. If we have a foreign key on a table that points to the primary key in another table, well, how do we look it up in the target table? Well, the primary key index. We already have that. We can get to it very quickly. But what if we want to go across relationships in the other direction? How can we do that without having to scan the whole table? Well, we do that by having an index created for every foreign key. So in not all but most relational database products, when you ask for a foreign key constraint, okay, it will build a foreign key index automatically. So in MySQL, you don't have to ask for foreign key indexes. It's enough to identify the foreign key with a foreign key constraint, which we're going to learn about in the next chapter, and the index is automatically built. Okay, what other kinds of indexes are there? Well, there are indexes that enforce unique constraints. And we're going to learn how to create a unique constraint in the next chapter too. But how do you make sure that when you go to add a value that it's not a duplicate of one that's already there? Well, you could do two things. One, you could scan the table, which could be very long and very costly. Or two, you could look in the index and see if there's already an entry for that value. So again, in MySQL and in most, if not all, relational database products, if you create a column and you say it's unique, MySQL will automatically generate a unique index on that column. Okay, so the real question is, when do we create more indexes than we get automatically? Okay, that's to get back to the slide at hand. So if we have a column that is frequently used in search conditions or joins, we might want to have an index built for that column. When the column contains a large number of distinct values, which is to say, if it doesn't, then the index is not very valuable. Okay. And when the column is updated infrequently. Okay, so if we have a column that, let's just go through these, that's not used frequently in search conditions or joins, and it has very few distinct values like male and female, or yes or no, true or false. Okay, and it's updated frequently, then we probably wouldn't want to build an index on that column. Okay. Why do we care that it's updated frequently? Well, every time we change a row in our table, we not only have to change the row itself, we have to check all the indexes to make sure that they're still correct. Okay, so that's work. Okay, so if you have a column that's updated frequently, well, then the index will have to be updated frequently as well. When the column contains a large number of distinct values, so if we have a lot of distinct values, well, then looking through the index is going to take us pretty quickly to the row that we're looking for. If, on the other hand, we have only a few distinct values, and you ask the index, can I have a list of all the females? Well, that'll help you to some degree, but it'll be an awfully long list. Okay, so if you need to narrow it down even further, did you really gain a lot by having that index? Maybe not. Okay. And of course, if you're not using it frequently in search conditions or joins, then you can just let the database server worry about that field. Pretty typically what we do is this. We take all these sort of automatically generated index for primary keys, foreign keys, unique indexes. And then we wait and see how well our queries run with just the basic indexes. And then if we're not getting the performance that we want, then we'll go experimenting with additional indexes, okay, in order to improve the performance. So I talked about a bunch of normal forms. We have two slides here. The first one takes us up to third normal form. The second slide has us going all the way through sixth normal form. Um, so uh, let's look at the first three normal forms. So it says the value stored at the intersection of each row and column must be a scalar value, a single value, and a table must not contain any repeating columns. So this means two things. One is that we're not allowed to store a list in a column. Okay, that's not a proper column. All right, because it's not the relational way, and we're not allowed to have repeating columns. Okay, what's the relational way? Well, we add more tables. Okay, we put things that repeat or are lists, which kind of repeat, into tables. And so the repetition factor uh, gets transferred to the rows. Okay, so first normal form, why do we have that? Well, because things have to be done the relational way. Second normal form, every non-key column must depend on the entire primary key, which is to say that we don't put columns in the wrong place. Okay? So, for instance, we might say that the vendor name is associated with the invoice, okay? Because we do need the vendor name for each invoice, okay? But it's not really associated with the invoice in a almost existential way. Okay. Uh, the invoice number is something that's only about the invoice. The invoice date is only about the invoice. The vendor number is primarily about the vendor. It's just the relationship between the vendor and the invoice is an important fact associated with the invoice that in the relational world, we model with a foreign key that points to the vendor. Okay, so second normal form is an easy version of only put columns on the table where they belong. Third normal form is an even more subtle version. Okay, I would say that third normal form says think very hard about where these columns actually belong. Okay, because you might be fooled. Okay, but so first normal form, do things the relational way. Second normal form, put columns on the right table. Third normal form, don't be fooled by tricky situations that might trick you into putting columns on the wrong table. All right. And most designers who are designing these databases for online transaction processing systems, which is what we're doing here, are going to stop at third normal form. Now, are there more normal forms? Sure, there are. So, Boyce Codd, fourth normal form, fifth normal form, domain key normal form, sixth normal form. Oh, they're the same thing. Sixth normal form and domain key normal form. Okay. Um, each of these things squeezes a little bit more redundancy out of the design. Okay. Now, um, every time we squeeze more redundancy out of the design, we put things into more tables. And when we go to use them, when we do a select, it takes more processing time to reassemble the data. So the question is, uh, how far do you have to go in order to do it the relational way and avoid enough duplicate data that people consider that you're doing a responsible job? And the answer is third normal form. And that's what we do in our class. Okay. So, what are the benefits of normalization? Well, let's see what the claims are here. There are more tables, and each table has an index on its primary key. That makes data retrieval more efficient. Well, I guess it does. I'll say I agree. Next, each table contains information about a single entity. That makes data retrieval and insert, update, and delete operations more efficient. Okay, so I'm going to say that that makes insert, update, and delete operations more e- efficient. Sometimes that makes retrieval harder because, as you know from back in chapter 4, we need to reassemble the data with a bunch of joins, and that's actually not a benefit, that's a cost. Um, so I'm not sure I would put the retrieval on that list. Next, each table has fewer indexes, which makes insert, update, and delete operations more e- efficient. Which is, if we had a lot of redundant data, we'd have to index it everywhere that we had it. But because we break it down and we put all the data related to one entity type on the same table, then we get a lot of use out of, for instance, the primary key index in each of the tables. And last but not least, data redundancy is minimized, which simplifies maintenance and reduces storage. So that's really true. So the original reason why people wanted to reduce redundancy, uh, probably the primary thing was the storage that data took up. You know, the cost of disk uh, storage has gone down dramatically over the past, well, certainly 40 years that DB2 has been around. Relational databases have been around. Um, uh, Now, the other thing is, as soon as you have a redundant fact that's in the database, you you have the possibility of getting the facts out of sync with each other. This can and does happen. So as soon as that happens, users lose confidence in that data. And so what happens is that the viability of the database as a tool for your operations goes down uh, because of broken correlation in redundant facts in the database. And so it's generally thought that if you just don't have the redundancy, well, then you can't have the problem that things got out of sync. And so confidence in your database is going to remain very high. Okay, so now we got some more normalization stuff. So this is invoice data again, related to the AP database, unnormalized. So let's see. So we have an invoice data with a column that contains repeating values. So this is a lot like the prior version that we saw, except item description, instead of having a bunch of repeating columns, we've created a list, and that's not the relational way. So that's a violation of first normal form. Or we could have it with repeating columns, which we've already seen before. That is a violation of first normal form because it's not the relational database way. Okay, so those both break first normal form because they're not the relational way. The invoice data in first normal form. So we've got Connor's public, so we have the vendor name, the invoice number, the item description. Okay, that's fine. Uh, the complaint I have about this is we have redundant values under vendor name. And if we were to replace this with a vendor ID, which would be a foreign key that pointed at the vendor's table, then we could go get the vendor name from that table, and each vendor would only have a single value there. So let's say this next version is the invoice data in first normal form with keys added. So we have invoice ID. Oh, so we can see that the first three rows all have to do with invoice 1, then 2 for invoice 2, then 1 for invoice 3. Okay. And because we did that, we're showing what the invoice sequence is. It's showing which line on the invoice it is. Okay. We still have the problem that we have a lot of redundant data in vendor name. And we're also not controlling values, right? So this, when we have these text columns, like the two that we see now, vendor name and item description, not only do we have the possibility of redundant values, but we also have the problem is that we're not controlling values against a fixed list of values. Okay, so now we've got invoice data in second normal form. So we have invoice number, vendor name, invoice ID. So we have invoice ID, invoice sequence, item description. Okay. So the first table that we're seeing is some version of the invoice or invoices table. And the second one is sort of the invoice line table. Okay, and then they kind of stop doing that. Okay, so let me back up and say what I would fix on this. Okay. So what I'm seeing here of these tables is the vendor name. I don't. Again, I don't think the vendor name belongs on the design of the invoices table or invoice table. We should have a vendor ID, and then we can get the vendor name off the vendors table. And that'll do two things. One, it'll reduce the redundancy here. Two, it'll control the values. Okay, so then we can only add vendor IDs for vendors that are in the vendors table. One thing that's interesting about the accounts payable database is that they do have a field that on the second table here, this item description. They never decide to have an item description table. I guess they feel that they buy so many different things that are called so many different things on vendor invoices that having a table of these that they have to code to and put a foreign key into is not useful for them. Okay, you'll find that they do have an account code from their general ledger accounts, so they do code it to a controlled list of general ledger accounts. But this item description column is a free text column. And this is something that you probably ought to be suspicious about. Free text columns, one, they can be redundant, and two, we're not controlling values. Okay. Now they thought about this and they decided it was okay. These things were going to be different enough, and they weren't ever going to want to look them up by that by their names in any kind of systematic way. So they decided that this kind of plain text column was acceptable. Okay. Um, it should really be your last resort. Okay. What happens is that these things become comments, right? Plain text fields really become comments. And they looked at this and said, well, these are really comments. This is a comment about what we bought on that line. Okay, it's not something that we're going to be able to. Uh, we're not going to want to analyze that text. Okay, I'll buy it. So this is the AP system in second normal form. So you have invoices and invoice line items. Okay, and then they go through some questions here about the second normal form, and they talk about are things in the right place. So does the vendor information depend only on the invoice ID column? Does the terms column depend only on the invoice ID column? Blah, 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 blah. Okay. Now, I just want to pause here and say there is a school of database design that says the following thing. You start out with a bad design. You start out with something that is completely unnormalized, and then you keep improving it. So you got to get it to first normal form, then you get it to second normal form, then you get it to third normal form. Now, I've always thought that was wrong-headed. Now, I'm probably in the minority here, so you can quote me at your own risk. But it's certainly the first normal form stuff, repeating groups and repeating values inside columns or lists, right? They're just not the relational way, okay? So it get rid of them. Everything else has to do with are they on is the column on the right table, or how finally do we need to break down tables? Okay. Um, this kind of idea of uh, is a column fully dependent upon the primary key or only partially dependent on it? I've got to tell you, these all add up to one thing. Is this column, does it belong on this table? And the answer to that is, does it have to do with the entity type that we're talking about? So if we go back to, let's see what we've got uh, here where we have invoices and we've got vendor name. Does vendor name really belong to invoice? Not directly. Or the vendor address or the city or the state. These are all in the wrong place. Okay? And are they in the wrong place because of second normal form or third normal form or fourth normal form? They're just in the wrong place. Get them out of there. Okay? So this we build up the design from one stage of badness to a less stage of badness to a lesser stage of badness up to some kind of point. Um, I don't think it's a good use of time, personally. All right, and this is the database when they get the third normal form. Now, I just want to point out here, this database has some weird structures in it, and that is, generally speaking, when we do a design, there's only one way to get from one of the tables to the other table. Okay, so the central way that we do this is, well, I'll back up. Okay, so the question is these general ledger accounts. Okay, uh, the general ledger account is on each invoice line item. Okay. Okay, so then why is there relationship to vendors as well? Well, it turns out that there's a default account number. This is to help us in the user interface to uh, put up, as soon as we put up that vendor, um, it's going to maybe pre-populate the account field to that default account number. Okay. And maybe 9 times out of 10, we're not going to have to change that. That helps. Okay. So this is not really the same database fact as this is. This this account number is a fact that says what account applies to this invoice line item. So it's factual, it's historic. And the relationship between vendors and general ledger account is prospective and it's predictive. Okay, and it's just there to make the the user interface go well. Okay, generally speaking, there's not two ways to get around the diagram. Okay, um, and we have another feature here with the default terms ID. That again, that's predictive. Okay. Okay. Now, the fact is, you can go further in breaking down tables and getting rid of redundancy than maybe you have to. So this is all the way out to fifth normal form. Okay. So for instance, um, we've decided that zip code is going to be a foreign key that points to the zip code table, and we're going to keep the city and state in the zip code table. Okay, well, we could do that. Um, we could decide that we want to do that with area codes. Now, what's good about these? Well, what's good about these is you're controlling values. Okay, and there's certainly people who do this in their design. Okay, there are other people who don't go this far. All right, and in fact, when you look at the design of the APE database, it does not go this far. Okay, it's back here. All right, so you can keep going even farther uh, than you have to. And then again, you have to remember every time you reassemble these things, every time you go to use them, okay, that's more tables that you have to join. Okay, so the question is, uh, where does the payback, what's the right place to stop? So the right place to stop for most people for these online transaction processing databases is to not go this far, um, not go to fifth normal form, to stop at third normal form. Okay, where we've got the zip code and the state and the city up here, and I think we have the telephone number up here somewhere as well. Okay, good. When to denormalize. So when a column from a join a table is used repeatedly in search criteria. If a table is updated infrequently, include columns with derived values when those are used frequently in search conditions. Okay, so when to denormalize? When you absolutely have to. Okay. Here's another place where you might want to denormalize. Okay. Um, there's generally an inverse relationship if, between uh, how much redundancy is expressed in your design and how much computing power it takes to generate an analysis of that data. Okay, so when we're when we're working with online transaction processing databases, we have a really uh, the, we're keeping the records of the organization. We want to make sure that they're correct. We don't want any situations where we can have conflicting, redundant values. Okay, and we're willing to pay the price of having to do, for instance, more joins and more computing in order to get the reports that we want out of the system. When we move on to more data warehousing and analytical backend stuff, okay, we're not changing the data all that often. It's often historical data, okay, and what people tend to do is that they denormalize their database design uh, as a way of making some of the analytics and the reporting more easily computed. Okay. And why do they think that's okay? Because nobody actually changes the data in a data warehouse. They rebuild it from these other online transaction processing systems at some regular frequency. Once a month, once a week, once a day, twice a day, 3 times a day. Okay? So the normalization that we're learning about here is for online transaction processing systems. Okay, you would want to denormalize. You might want to denormalize drastically if you were creating a data warehouse application. Okay, and this page that we have here is Workbench, MySQL Workbench, and what we have here is a bit of a tour of the diagrammer. Okay, and up until now, we've been uh, we've been opening up connections, and we've been working with that part of the tool. And now what we're doing is, we're clicking on this diagram, and we're either picking one of the models we already have, or we're clicking on the plus to say we want to create a new one. Okay. Um, the diagrams that we have, the kind of models that we have, are called EER, uh, extended entity relationship. What's extended about entity relationship? Um, uh, there's more data on these things than would be in a typical. There's more details on these things that would be available in a typical uh, data conceptual data modeling entity relationship diagram, but you can think of these EERs as ERDs, entity relationship diagrams. The kind of things that you could do is you can open an existing one, you can create a new blank one, you can create one from an existing database. You can have it create one from a script that creates a database, okay? And you can remove one of these from the list, essentially a delete. Doesn't want to go to the next one. Um, when you uh, when you uh, when you open it up One of the things that you need to do is you need a new diagram. So this add a diagram thing, you can double click on that and get a new diagram. What can you do? You could uh, add a new table. You could delete a table. You could display a diagram, create a new diagram, create a database creation script from the model. You could edit a table, add a table, delete a table. Okay, this is what the tables look like. If you're in my class, you've already seen tables that were generated out of this tool because the diagrams that I've showed you for the databases that we've been using have come out of this tool. I thought we were just there. No. So let's say operations. Didn't we have that there? No. Okay, that's a different slide. Operations for working with an ER diagram. Add an existing table to the diagram. Add a new table to the diagram. Display the model for a table. Define the relationship between two tables. Edit and delete relationships. Remove a table from the diagram. One important thing to remember about this kind of diagrammer is that it's got it has a data model. Okay, so there is a model. So you create tables and they have relationships with each other. And then you can pull those out onto diagrams. Okay. So one of the things you have to really be able to distinguish between is a change you're making to the diagram and a change that you're making to the model. For instance, when you go to delete something from the diagram, it essentially, I forget the question it asked you, but it's essentially saying, oh, do you want this table, do you want to leave it in the model, but just not show it on the current diagram? Or do you want to take it off the diagram and delete it from the model? I have a lot of students who think that they've deleted a table, so they're working and they come up with a version of a table and it gets all bollocksed up and they go, well, let's get rid of that. Let's create that again. Well, if you answer the questions the wrong way when you go to delete it, you'll get to the end and you'll have 4 customer tables, only one of which is on the diagram. Okay. So in fact, if we back up here, this part of the diagrammer will show you what the tables are that are in your model. Okay, so if in fact you have accidentally created 4 customer tables, if you go down this list of tables for the model that you're using, you will see that it's got 4 customer tables. So we have the model that we're working with, and then we have the diagram. Pretty much we only make changes when we're over here and we're playing with the diagrammer, but again, you can get your diagram and your model out of sync, so you ought to be thinking about that. I've got at least one, and from time to time I have more tutorials on how to use a diagrammer. So I'm not going to do that here. And that means that's the end of the chapter. And so I'm going to say bye until next time. Bye bye.